Welcome everyone. This is the video for section 10.4, concept video, areas and lengths in polar coordinates. So we are first going to find out area for a polar curve. So for that, we are going to refer to our geometry that we know about area of a sector of a circle. So if you have a slice like the way shown in figure 1, and the radius of that sector is r, which subtends an angle of theta, then area of the sector of the circle is given by the formula half r square theta, which we know from our geometry class. So where r is the radius and theta is the radian measure of the central angle. So now what we are going to do is we are going to take the polar curve as shown as r equal to f of theta here. Um, the curve is not as neat as the area of the circle boundary. And then it is going to be bounded by theta equal to alpha and theta equal to a and theta equal to b. And we are going to find out the area inside of the polar curve. So it is under the polar curve bounded by the radial lines theta equal to A and theta equal to B. This is the area we are going to find out. So the idea is similar to any Riemann sum method that we have seen before. If f of x is a graph given, and if you want to find out the area bounded by the lines x equal to A and x equal to B, what you do is you divide this into number of subintervals A to B, which are of equal width, and then we divide them into either rectangles or there are several methods we have done, either rectangles or trapezoids or parabolas and things like that. Then we can find out the areas of this rectangle and add all the rectangles. That will become the Riemann sum. Then the Riemann sum will turn out to be the area under the graph, which is integral, definite integral, which is actually the left hand points, right hand points method, and all that we have seen. So it is limit as n approaching infinity, I varying from 1 to n. So this can be used as left hand point or right hand point or midpoint or trapezoidal rule or any of the approximation methods that you have seen. So the idea is to write the definite integral as sum of the areas, right? Area under the graph as sum of several areas. That's the same idea here also we are going to use. Let R be the region as shown in figure 2, bounded by the polar curve r equal to f of theta and by the rays theta equal to a and theta equal to b, where f is positive continuous function and where b minus a lies between 0 and 2 pi. We divide the interval ab into number of subintervals with endpoints theta 0, theta 1, theta 2, theta n, and so on, and equal with delta theta, just as the way we defined in Cartesian coordinates. The rays theta equal to theta I, then divide R into n smaller regions with central angles delta theta, which is theta I minus theta I minus 1. So one sample is shown here in this graph figure 3. So it is divided into number of subsectors, and then we are shown one of such um, sector. Then delta AI is the area of the ith region approximated by the area of the sector of the circle with central angle delta theta and radius f of I theta star. So if you take any value of r, it will be f of theta I star in the interval theta I minus 1 to theta I. We use that and find out the area of that particular sector, bounded by theta equal to theta I minus 1 and theta equal to theta I, we get this area. So it's kind of similar to the idea of half of r square theta. So it is for that piece, the area is given as delta AI, the area of the ith sector, which is half f of theta I square delta theta. Then we can do this for every sector and add them all. That will give a Riemann sum, the way we have seen, we are seeing here. Then this can be extended to, as n approaching infinity, this Riemann sum would become and a definite integral a to b, half of f of theta square d theta. The formula for area A of the polar region R is A equal to integral A to B, half of f of theta square d theta. The easy way to remember this is this is often written as A equal to integral A to B half r square d theta. The understanding here is r equal to f of theta, which is the polar graph. So area of the polar curve, area under the polar curve bounded by the radial line, area inside the polar curve bounded by the lines theta equal to a and theta equal to b is given by this definite integral a to b half r square d theta. We'll take an example based of this information. Find the area enclosed by one loop of the four-leaved rows r equal to cosine 2 theta. So please refer to the graph that we did elaborately refer to this graph in section 10.3. We actually graphed this one. First, the Cartesian graph was done, and then we had to convert this to polar graph. So this particular graph, I would like you to refer to this previous section. First, you have to graph that using the techniques that we used in the previous section. Then you have to get to this area. Because it's one loop, you can consider that to go from negative pi by 4 to pi by 4. So we are only considering the area inside of one loop. So area of one loop is given by integral a to b, just negative pi by 4 to pi by 4, half r square d theta. So it is integral negative pi by 4 through pi by 4, half, what is r? R is given by cosine of 2 theta, that is given in the problem. So you use that to write r square, which is cosine square 2 theta d theta. And this is an even function. So half can be taken out, and you have negative pi by 4 to pi by 4 of an even function. The function is even. The integrand is even. So you can multiply. So we can use the property of one of the integral property. So if you have negative a to a, fx dx will become twice integral 0 to a fx dx, provided f of x is even. So cosine square being even, we can write this as half of and twice integral 0 to pi by 4. So we are writing negative pi by 4 to pi by 4 as twice integral 0 through pi by 4. Twice integral 0 to pi by 4 cosine square 2 theta d theta. So 2 and 2 cancel out. Anytime you have an even cosine or even sine to integrate, you're going to use the trig identity. So 0 through pi by 4 by using double angle. So twice double is 2 times double is 4. So it will be 1 plus cosine of 4 theta over 2 d theta. So we are using trig formula, double angle formula. So you can take the half out, then integrate. Integrate it is theta. Integral of 1 is theta. Integral of cosine 4 theta is sine 4 theta over 4 between the limit 0 and pi by 4. So it is half. Then theta is replaced by pi by 4. Sine of 4 times pi by 4, that would be 0. The lower limit is 0, so it is pi over 8. That is the area of one loop. So is this the only way to do this problem? Because the question is only finding area of one loop, you can also consider and all the areas between 0. The graph is drawn between 0 through 2 pi. So you can also do the following method. As area of each loop is the same as the other, we can consider this to be 1/4 of the area of the complete polar curve. So area of one loop is 1/4 of the area of the whole thing. So it is 1/4 of 0 to 2 pi of the entire graph. Entire graph is going to be, what is the equation of the graph? R equal to cosine 2 theta. Half of r square d theta. So that will be 1 over 8 integral 0 to 2 pi. Cosine square 2 theta is 1 plus cosine of 4 theta over 2 d theta. It becomes 1 over 16. Integrate, that will be theta plus sine 2 theta over 2. Then it's 1 over 16. Apply the upper limit, which is 2 pi. Upper limit for sine 2 theta is 0. Then the rest of them are 0. So it is pi over 8. So you can do this only when all the areas are equal, the graph is symmetric. Okay, so then you can do 1/4 of the area of the whole thing in this particular case. So there are two ways to do this problem.